our seminar series. My name is Ivan Aiello, and I'm very excited to introduce you. So let me say a couple words about Manny, and then we'll definitely start with his talk. So first of all, Manny is one of our colleagues on the main campus. He works in the geology department. He just started as department chair at geology.
Yep.
Yeah.
You get very little praise as department chair. You gotta take it where you can get it.
You get hugs and kisses every day.
Yeah.
That's what I get.
Right.
And so, so Manny is a geomorphologist. So he's a special kind of geologist, probably a better kind. So he looks at shapes. That's what geomorphology is about. And he has been looking at changes in landforms across different scales and spatial and temporal scales here in California. He's worked pretty much everywhere in California, looking at landslides and including the geomorphology of the coastline. We were just talking about that. So it's very interesting into looking at landforms. And let me tell you a little bit about his very long CV here, which so he got his BA actually UC Berkeley in anthropology, right?
Yep.
Anthropology. Then he switched to a master's at UC Berkeley again in geography. And finally, he's got his PhD at UC Santa Barbara, maybe in 2002. We don't remember, but around that time. He was actually hired at San Jose State University at the same time I was hired. So we have kind of parallel lives. And he now lives in Santa Cruz. And you can see that he's a very active surfer. So the story that he's presenting today is about the age of the uplift of this Sierra Nevada. And for those of you guys that are in my classroom, in my marine geology class, you know that's a pretty important event in California geology. That's when the volcanic arc that used to be, developed all in the back there got, ended, and the roots of the volcanic arc got exposed. And so the timing of that has been always a big debate. Until a few years ago, we thought that was a pretty young feature, but Manny will show you how there's evidence that it might be much older. Okay, well, thank you so much for giving me your talk on the real geological history of Stanislaus Table Mountains and Yosemite Valley.
All right, thank you for that introduction. Is this on? You guys can hear me okay? Yeah. Okay. So Ivano is referring to a little bit of the background here. So it's been thought for about the past century and a half that the Sierra Nevada is a relatively young range, having only uplifted in the past 5 or 10 million years. And that's been the dominant paradigm for a long time. And it's really only in the past few years that people have started to question this paradigm. And so I'm going to go over some of the evidence that people have used to argue for the Sierra Nevada being a young range, and then I'll show you why that evidence isn't as strong as some people would think. So the first bit of evidence that we're going to look at is the Table Mountains. So this is in the Stanislaus River watershed, and you can see this ribbon of kind of this flat-topped ridge. And if it looks like a river, you're right. And so this is zooming in on it a little bit. And again, you can see how flat it is, how it kind of looks like a river. And this is actually a lava flow. So this is known as the Table Mountain latite. And so this was looked at and studied fairly early on in kind of the history of the geology of California. And what we're going to be looking at are geologic cross-sections. And for those of you who aren't familiar with what a geologic cross-section is, it's just basically a slice of the cake. So we're going to be looking at a slice through the crust. And so this is the original theory for how the Table Mountains formed. So the idea is that something like 10 million years ago, so the Table Mountain lava flow happened 10 million years ago. And it's thought that lava flow came down a bedrock valley. So the idea is that there was a valley or a canyon that was cut in granite, and the lava flow just traveled down through that valley. And since then, the granite ridges on either side have eroded down, leaving the lava flow up in this elevated position. And so this was J.D. Whitney's kind of first stab at this theory. It's known as topographic inversion, and you can see why. It's because what used to be low is now high, and what used to be high is now low. And to cut down through all this granite, you have to basically erode about 1,000 meters of these ridges to leave the lava flow up in its elevated position. So how do you get 1,000 meters of erosion through granite? Granite is pretty tough stuff. And so the thought was that this was diagnostic of recent uplift. So to erode all this granite, you needed something to accelerate erosion rates, and the idea was that the only way you could do that was through uplift. So since the lava flow is 10 million years old, that means that the uplift had to have happened sometime in the past 10 million years. And this is the standard theory for the evolution of the Table Mountains. And in fact, so this is a textbook written by Debbie Harden, who ironically is the person I replaced at San Jose State. When she retired, I got her position. And so this is what she wrote in her textbook. As a result, the topography has become reversed or inverted, with former valley bottoms now the highest part of the landscape. And then down here, the volcanic flows, blah, 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 provide evidence that the present Sierra Nevada mountains are very young by geologic standards. And so, like I said, this is the standard explanation. This is what everybody believes. So, but let's take a look at the actual evidence. This is a little out of sequence. Nope, okay, so just to give you an idea of where we are. So here's San Francisco, and we're going to be looking at this area right here. So here, this is that Table Mountain latite flow running from the Central Valley, essentially up into near the crest of the range. So backing up. So this is zooming in. Again, in black here, we've got the Table Mountain latite, which presumably followed this bedrock valley. And so we're going to look at this area right here, this site right here called the Dardanelles West. So this is another one of those slices down through the crust. So in black here, this is that lava flow. That's sitting on some younger volcanic rocks, or some older volcanic rocks called the Merton Formation, which we'll talk about in a little bit. And these volcanic rocks are maybe like 15 million years old. And then these older rocks are on top of an even older volcanic formation called the Valley Springs Formation. And the Valley Springs Formation, these are big ash flows that came in from Nevada something like 30 to 40 million years ago. Now, what's interesting about this site is that there's also Valley Springs Formation here and here. And so it's difficult to imagine how this latite could have been laid down in a bedrock canyon that would have looked something like this if we have these older volcanic rocks sitting in a lower position. So there's no way you can create a bedrock ridge here on either side of this lava flow to create a canyon. So this gives you an idea of this Merton Formation right here. And so the idea then is that instead of this lava flow coming down through a bedrock landscape, it actually came down through a landscape that was completely buried by these volcanic rocks here. And so these are known as lahars. So they're basically volcanic mud flows. They're a combination of volcanic rocks and mud and water, just like we see right here coming out of Mount St. Helens. So imagine this stuff just burying this entire bedrock landscape, and then this lava flow flowing down a channel cut in these volcanic rocks. Okay, and we'll see that this is kind of a recurring theme as we follow this lava flow down the range. Oops, okay. So again, so here's that same site. This is the Dardanelles. So all this white stuff, of course, is bedrock, and this is the Table Mountain latite. Up here, here's that Mertens Formation, those volcanic mud flows, and then the Valley Springs Formation is lower down. But imagine this entire bedrock landscape just buried in these lahars, these volcanic mud flows. Whoops. Okay. So traveling down a bit, so we were up here at Dardanelles, now we're at this site right here, Vallecito, and we see the same kind of situation where we have the Table Mountain latite at a relatively high position in the topography, but much older sediment lower down. So here in gold, these are the tertiary gravels. These are the gravels that the gold miners sifted through to find gold. These gravels are something like 40 to 50 million years old. So you have much older sediment stratigraphically lower than the latite. So again, there's no way you can put a bedrock ridge somewhere like this on either side of this latite that this lava flow could have come down. So clearly, this was a landscape that was buried in sediment, and this lava flow just flowed down over sediment, not bedrock. And, oops. So now we're going to look at this site right here, Parrots Ferry. And you can see the latite right here. Right, so there's that flat top ridge, and it's sitting right on top of bedrock. And this was actually one of the first sites that J.D. Whitney and his colleagues looked at and posited this idea that this lava flow was actually flowing down a bedrock valley. If we actually look at this area in detail, so this is the bedrock right here. Here's the diorite. It's kind of a type of granite, a granitic rock. Here's the latite. That latite is actually draped over a ridge. So this is not a valley bottom. The latite didn't follow a valley bottom. This is actually a flow that just basically buried this entire landscape and was just kind of draped over this ridge. So there's no topographic inversion here. If this was topographic inversion, this wouldn't be a ridge. This would be a valley. And then the last site we're going to look at is this down here, a little bit further down. And same kind of thing. Here's the Table Mountain latite, and it's not on bedrock. It's not. There's no evidence that it traveled down a bedrock valley. And again, it's just sitting on much older sediment, and there's just no way to create a bedrock ridge here that this lava flow could have followed. So instead, what it looks like is that this entire valley here was just buried with sediment, and the latite just traveled down, that lava flow just traveled down a channel cut into sediment, not bedrock. And so here's the real story for the Table Mountains. So 10 million years ago, you've got that bedrock way down here, but what's more important is that this entire landscape was buried with sediment, and there was some channel cut in that sediment, and that's what the lava flow followed. And then the sediment eroded, and sediment is a lot easier to erode than granite, so already this makes a lot more sense, and that's what left behind the Table Mountains. So kind of the conclusion here is that you don't need uplift to create the Table Mountains. Again, because cutting down through sediment is just so much easier than cutting through granite. Okay, so that takes us to Yosemite. So here's, again, this is a standard theory for how Yosemite Valley was created. So the idea is that back before, say, 10 million years, the Sierra Nevada was kind of a low range with gently rolling hills, and some kind of drainage networks cut into these low rolling hills. And then about 5 to 10 million years ago, the entire range tilted up, and as a consequence of that tilting, the rivers got stronger, they got steeper, they got stronger, and they cut deep canyons throughout the Sierra Nevada. And if you've been in the Sierra Nevada, you've all seen these deep canyons. So at a surface level, this makes some sense. So I decided to actually look at that theory in more detail to see whether that can explain Yosemite Valley. And of course, if you've been to Yosemite, you know it's a deep valley. Just to get you situated in terms of features that we're going to be talking about, so kind of Yosemite Valley proper is right here. If you've been hiking in Yosemite, if you've driven up through Yosemite, this is the Yosemite Valley. The Merced River follows down through here like that. This valley here, this is Little Yosemite Valley. So the Merced River, the upper reach of the Merced River flows through Little Yosemite Valley. And then there's a tributary to the Merced River, which is called Tenaya Creek. And Tenaya Creek drains another deep canyon called Tenaya Canyon. And so how many of you have heard have heard that Yosemite Valley was cut by a glacier? Okay, so quite a few of you. And that's, everybody thinks that. So there's no shame in thinking that. And so this is a standard theory for how Yosemite Valley was created. This is right from the USGS, so the United States Geological Survey website. So this is the officially sanctioned story. So about 15 million years ago, the Sierra Nevada was this kind of low mountain range with gentle rolling hills. And then about 5 to 10 million years ago, uplift happened. The rivers got steeper, they got stronger. They cut canyons down into these kind of broad valleys. And the canyons got deeper and deeper. And so this is kind of an important thing because Yosemite Valley, we know that Yosemite Valley was already deep before the glaciers. So we haven't even hit the glaciers yet, and we see that Yosemite Valley is already a fairly deep canyon. And then the glaciers came, and so the idea is that the glaciers widened Yosemite Valley, but Yosemite Valley, again, was already fairly deep. And then the glaciers receded, and that leaves the landscape that we now see. So really two important things here. First is that Yosemite Valley and also Tenaya Canyon were already deep before the glaciers. So that's already fairly well established, and I'll show you some evidence for why that is. But they were deep. They were deepened by uplift. So you had this period of uplift about 5 to 10 million years ago that is responsible for this deepening. So this is one of the reasons why we're pretty sure that Yosemite Valley and Tenaya Canyon were already deep before the glaciers. So this is Tenaya Canyon, and so Yosemite Valley is just right down here. And Tenaya Canyon is V-shaped. And so it's pretty well established in geomorphology that if you have a canyon that's V-shaped, that means it was cut by a river. So U-shaped canyons, so canyons that are kind of look like this, those are cut by glaciers. V-shaped canyons, those are cut by rivers. And we know that at some point there was a glacier that came through here, and because we see evidence of that glacier's passage through this canyon. And so what that means then is that this canyon must have been cut by a river before the glaciers came. Okay, so that's kind of a key thing. Okay, so a little bit more geography just to get everybody situated. So here's Tenaya Canyon, which is what we just looked at. Little Yosemite Valley up here, and then the main Yosemite Valley right here. So Yosemite Valley, the eastern extension of Yosemite Valley is Tenaya Canyon. So you can kind of think of these two features as really the same feature. And you can see that again here. Here's Yosemite Valley, And it just looks like Yosemite Valley's natural extension is up Tenaya Canyon, and it's not up the Merced River, which is odd because the Merced River is a much bigger river than Tenaya Canyon. And we'll see kind of some why that's weird. So if we look at a topographic cross-section across here, across Tenaya Canyon and Little Yosemite Valley, we see that these two valleys are quite different. So here's Tenaya Canyon. It's very deep, it's very narrow, it's V-shaped. And here's Little Yosemite Valley. And the difference between the two is about 800 meters. So Tenaya Canyon has been cut almost a kilometer deeper than Little Yosemite Valley. And that's very strange because the Merced River's watershed, the Merced River runs through Little Yosemite Valley, is almost 3 times greater than Tenaya Creek. So the Merced River, which is coming through Little Yosemite Valley, is a much bigger river than Tenaya Creek. And in fact, so here's a picture of Tenaya Creek, and it looks impressive, but it's really not. It looks wide here and big, but it's actually fairly shallow, and instead it's just really wide. And the reason why it's really shallow is because Tenaya Creek has been unable to cut down through this granite. So instead of being able to cut down, the water just kind of spills out everywhere along the valley bottom. So here's another kind of weird thing. So we were looking at this area right here. Here's Tenaya Canyon, and here's our Tenaya Creek, and here's the Merced River. And we're going to focus our attention here on the South Fork of the Merced River. So this is what the South Fork of the Merced River looks like. And again, it hasn't cut a deep canyon. If uplift is responsible for Yosemite Valley, how come that uplift didn't cause incision of Little Yosemite Valley? And how come it hasn't caused any major incision in the South Fork of the Merced River? So what happened in Yosemite Valley and Tenaya Canyon is actually pretty unique for the area. We don't see evidence for deep canyon incision in these other valleys. So this is the first unsolved question, and this is a question that is not at all addressed by this uplift theory. So why is deep recent incision limited to just Tenaya Canyon and Yosemite Valley? So here's another weird thing. So this is the Merced watershed. Here's the Central Valley. Here's the crest of the Sierras. And here's the Merced River. There's Yosemite Valley. And so everything that's been eroded out of the Merced watershed has ended up in the Central Valley. So you can think of the Central Valley as essentially a big dumpster that just collects all the material eroded out of the Merced watershed. And so let's take a look at what's in that dumpster. So this is the lithological map. Anybody here know what the pink is? Besides Ivano? Any guesses? All this pink rock? Sierra Nevada? Yeah, it's granite. So it's granite. So you see a bunch of granite here, some blue metamorphic rocks, and then some other metamorphic rocks here. So this is all bedrock. This is all sediment right through here. And, oops. There we go. So you would expect to find basically a bunch of granite and a bunch of metamorphic rocks in the Central Valley right at the outlet of the Merced River. Instead, what you find, so I've zoomed in here, is a bunch of volcanic rock. All this orange rock here, this is that Merton Formation. This is that same stuff I showed earlier, where it's essentially composed of these volcanic mud flows. In this case, though, these are reworked sediments. So somewhere further up in the watershed, there was these volcanic mud flows that solidified, and then that stuff got eroded away and transported down to the Central Valley. Now, okay, yeah, so here we go again. So when you think Merton Formation, think of these volcanic mud flows, these lahars. In fact, so I calculated how much of these orange rocks there were here, this orange volcanic sediment, and it's something like 32 cubic kilometers. So this is a huge amount of volcanic sediment deposited by the Merced River. Just to give you a sense of what 32 cubic kilometers looks like, so imagine a big cube, 3 kilometers by 3 kilometers by 3 kilometers. All of that is just volcanic sediment. Here's the weird thing. No orange rocks up in the Merced watershed. There's not a single scrap of Merton Formation in this entire watershed. And this watershed has been mapped at very high detail, great detail. There's no Merton Formation at all in this watershed. So where did all this stuff come from? And so this is the other unsolved question. Where did all this volcanic rock come from? If there's none of it in them, we know it's carried by the Merced River, but none of it is actually in the Merced watershed. Again, this is not a question that is answered by the uplift theory. And so here's another weird thing that's going on in the Merced watershed. So just to give you, again, a sense of what we're going to be talking about. So here's the Merced River. It comes up through here. Here's Tenaya Canyon. I'm sorry, not the Merced River, the Tenaya Creek. Half Dome is right here. And if you go up a little ways, you end up intersecting the Tuolumne River. So here's the Tuolumne River coming up this way. Tuolumne Meadows is up over here somewhere. Tuolumne Canyon. And you'll notice this interesting little canyon right here that's drained by Cathedral Creek. And so here's what it looks like in, on a hillshade. So the Tuolumne River right through here, Cathedral Creek right through here. And, whoops. And so Cathedral Creek is draining a canyon that's almost as big as the Tuolumne River. It's almost as deep. There was never a glacier that came down through here. But Cathedral Creek, just like Tenaya Creek, is a tiny creek. There's not a whole lot of flow, and it's difficult to come up with some mechanism that this small creek could have cut such a deep canyon through very resistant bedrock. So that's kind of a weird thing that's going on with the Tuolumne drainage system. Another weird thing that's going on with the Tuolumne drainage system, so here's the Tuolumne River. You follow it like this. Anybody notice anything weird about the tributaries coming into the Tuolumne River? Or just like the overall pattern of the Tuolumne River? So here's the Tuolumne River going like this. Like just looking at the tributaries. Yeah, the shape is weird, but look at how many tributaries we have coming on this side. 1, 2, 3, 4, 5, 6, 7, 8, 9, and look how many we have coming in from the south. Basically 1 or 2. So there's this very odd asymmetry, and a drainage system should be leaf-shaped. So it should the main river should just go straight up like this. And then tributaries should be branching out pretty symmetrically from the trunk stream. That's not all the case with the Tuolumne River. It's very asymmetric, which means that at some point in the past, it was getting a lot more flow from up here, from the northern half of the watershed, than the southern half. And so this is another very odd thing about the Tuolumne River drainage system. And so another unsolved question that is not addressed by the uplift theory: what cut Cathedral Creek, and why is the Tuolumne River network so lopsided? Okay, so we're going to come back to this idea here where we have the Sierra Nevada this bedrock landscape buried underneath volcanic rock. And so this is just a little sliver of what's left, but just imagine this entire landscape buried by hundreds of meters of volcanic rock. And you might ask, well, where did all that volcanic rock come from? Well, something that is often not recognized or appreciated is that from about 20 million years ago to about 5 million years ago, the crest of the Sierra Nevada hosted a chain of volcanoes. So just imagine a bunch of volcanoes sitting at the crest of the range and just delivering volcanic sediment, lava flows, lahars, just all this stuff pouring out onto the Sierra Nevada. And I should point out, this is mostly in the northern Sierra Nevada as far as we can tell. Okay, so the Sierra Nevada looked very, very different from than 15 million years ago than what it does now. If there are any skiers here, you might recognize this as Kirkwood Mountain. And Kirkwood Mountain, so this is all granite. Kirkwood Mountain, this entire mountain here is just all volcanic mudflow deposits. So this is all lahar. So this entire mountain here is what's left from the volcanic sediment that that once buried the entire crest of the range. And just to give you an idea of what these rocks look like, so this is a picture I took from the ski lift, and you can see it's just basically a mud flow. It's just a volcanic mud flow. You can identify all these individual rocks in here. And so this entire mountain is just composed of this stuff. And again, this stuff completely buried the northern Sierra Nevada under hundreds, many hundreds of meters of sediment. Okay. Well, are there any questions? I should have asked for questions earlier, but anything? No? Okay. Okay, so here is my theory that explains all these unsolved questions. So 20 million years ago, here's the Stanislaus River drainage network. Here's the Merced River drainage network. I think it looked pretty much the same as it does now, at least in terms of the shape of the network, not necessarily the depth of the canyons. And the Tuolumne River network, this is what it looks like now. Actually, not now, but this is what it might have looked like back then. We don't really know what it looked like back then, but it doesn't look like what it does now. And I'll show you why. So 10 million years ago, one of these volcanoes grew over kind of this southern part of, well, kind of over the headwaters of the Stanislaus and Tuolumne rivers. And so I'm calling this a volcanic edifice. So it's not necessarily just the volcano, but this is all the sediment, the volcanic apron that was just being deposited by all these lahars and all these other things. And there must have been a river draining this volcanic plain or this volcanic edifice that at some point linked up with Tenaya Creek. So, you can imagine that you've got this big volcano. It must have had rivers coming down it. One of these rivers must have linked up just with the kind of the head of Tenaya Creek. And so now Tenaya Creek is no longer a creek. It's a raging river. And not only does it have a lot more flow coming down it, but it's also bringing with it a lot of sediment. And one of the main ways that rivers can cut down through granite is that it's not actually the water that's cutting the granite, it's the sediment that's in the water. And so that's a process called abrasion. And so imagine a river cutting down through this volcanic edifice. It's carrying with it a lot of sediment, a lot of this volcanic sediment. That sediment starts wearing away at the valley that the Tenaya Creek was flowing through, and also Yosemite Valley, and just making it deeper and deeper and deeper, and cutting down through it. So, so that's what was going on about 10 million years ago, I think. And at the same time, this explains all the volcanic rock deposited in the Central Valley. Because now we have a source for all that volcanic sediment. It's this volcano that was sitting up here. So at some point, volcanism started to shut off in the Sierra Nevada. And once that supply of sediment the volcanic sediment started to slow down, then the edge of the volcanic edifice just started to erode backwards. And at some point, these rivers, or this river that was once feeding Tenaya Creek, started feeding into Tuolumne River. And in fact, probably a bunch of these rivers started feeding into the Tuolumne River, cutting new canyons, and explaining why all these tributaries are now facing northward, because really they were just being fed by these rivers flowing southward off this volcanic edifice. And then volcanism completely shut off, and now all that's left is just really bits and pieces of this volcanic edifice. So, for example, the Dardanelles site that I've already showed a few times, that's one of these little slivers of volcanic rock that's still out there. Same thing with Kirkwood, Kirkwood Mountain. That's just one of these little bits of this edifice that's still around. So just to kind of help you visualize this theory, so again, we have Yosemite Valley, Tenaya Canyon, Tenaya Creek coming up through here. And so there just must have been a river coming off one of these volcanoes, feeding into Tenaya Creek, and that's what cut Tenaya Canyon and Yosemite Valley. And so here's a little bit of an elaboration on that. So here's that river coming down through here, feeding into Tenaya Creek, cutting the canyon. And then at some point, probably just because of erosion, it got diverted into Cathedral Creek, and that's how Cathedral Creek was cut. And in fact, there's some interesting data here that I'm not showing, but you can measure the wavelength of the meanders. If you look at Cathedral Canyon, it's meandering like this. And based on the wavelength of this meander, you can estimate the size of the watershed that must have cut this canyon, the size of the watershed that must have created the river to cut this canyon. And that watershed is something like 1,000 square kilometers, which is much bigger than Cathedral Creek's present watershed. So pretty good evidence that whatever cut Cathedral Creek had a much bigger watershed or Cathedral Creek Canyon had a much bigger watershed than Cathedral Creek does now. And then if we play this forward a little bit more, at some point that river, again because of erosion and kind of the back wearing of this volcanic edifice, that river started feeding Tuolumne River, and that's what cut the Grand Canyon of the Tuolumne. And so here's some pretty good evidence. So here's the Grand Canyon of the Tuolumne. So this is, so imagine we're standing right here, and now instead of looking upstream, we're going to look downstream. And so that's what we're looking at now. So here's the Tuolumne River. And the Grand Canyon of the Tuolumne is also a very impressive canyon. It's very deep. There's a ton of relief. It looks very fresh. It looks very new. And if we look at this area right here, we see something very interesting. So we're going to zoom in on that. And what we see is this V-shaped canyon filled in with volcanic sediment. So this is all volcanic sediment right here. And so what we're looking at here, this is where the Tuolumne River used to flow before this whole mess started. So there's that V-shaped canyon, and so the Tuolumne River used to flow down through here. And that was before this entire area got buried in these volcanic rocks. The Tuolumne River used to flow through here, and we can actually trace it. It used to do something like this. And this is the modern Tuolumne River right here. So, so the idea then, is that when all that volcanism started, this kind of the proto-Tuolumne River that canyon got buried, and then the water was just flowing wherever, and then at some point everything got diverted into well, not diverted, but it started cutting this new canyon when the flow was diverted off that volcano. So this new theory solves this question, and this one, where did all that volcanic sediment come from? And then also it explains how Cathedral Creek Canyon was cut, and then also why the Tuolumne River network is so lopsided. And so some of the main conclusions from this study, from these two studies actually, is that the evidence that was used to argue for recent uplift is really more consistent with alternative hypotheses. There's just too many other things going on that aren't well explained by the theory of recent uplift. And in addition to that, this evidence is consistent with this idea that the Sierra Nevada is actually an ancient mountain range, popped up maybe as early as 65 million years ago. So the Sierra, when you look at the Sierra Nevada, that's a mountain range that was around potentially when the dinosaurs were just about to become extinct. So it's actually a very old range. It's not a recent range. And then another conclusion is, make sure you question everything, because this is, like I said, this has been the dominant paradigm for 150 years, and I can say as a scientist, there's nothing that brings me greater joy than proving other people wrong, and I think that's true for a lot of us. All right, well, thank you for your time and attention.
Thanks, Manny. That was really interesting. I had a question about Half Dome itself. So was that then formed, do you think, by the erosion of this ancient river going down there, or was that also, or some combination of that and the glaciers, or how do you think that feature itself formed?
Yeah. So Half Dome is complicated. Let's see. Yeah, Half Dome is another one of those things where there's this idea that so here's Half Dome. I mean, there's the relief is a little exaggerated here, but here's Half Dome. So there's actually a big fracture, a huge joint that runs along like that. And so the idea is that when Tenaya Canyon was cut, that Half Dome, that top part just probably started sloughing off due to rockfall. So it was just as Tenaya Canyon was being cut, Half Dome was just being undercut, and because you had that zone of weakness from that fracture, it's just mass wasting. Yeah, it's not as exciting as. Yeah.
This is very interesting. Thank you.
Oh, okay.
I learned a lot, and I'm curious now that you've presented this hypothesis. New paradigm.
Yeah.
How does one go about and test? Can you age certain things? Can you find, I don't know, age the rocks of the Sierra Nevada to see,
Yeah.
or look for volcanic
Yeah,
activity?
that's a great question. And in fact, so people have dated. There's something called thermochronology, basically. You can date, you can kind of measure how quickly rocks cool down. So when you have, let's say you have a big chunk of granite like this, and this rock is at a certain temperature, and then as that granite gets eroded, that rock starts cooling just because there's less rock on top insulating it. And so you can use that cooling rate to essentially measure erosion rates and figure out when that erosion happened, basically. And so that was done before my study, in fact, and they concluded that Tenaya Canyon in Yosemite Valley had indeed been cut in the past 5 to 10 million years, which they were psyched. They're like, oh, see, it was uplift. because it just matches the dominant paradigm perfectly. And in fact, I reviewed that paper. They sent it to me, and I was like, you might want to consider like drainage reorganization. Just have one line in there so you guys don't look bad when I publish my paper. And they did, and to their credit, they did. So there are ways of doing that, but to actually figure out what caused the incision, that's a little more complicated. But you can't ignore the fact that you have 32 cubic kilometers of volcanic rock carried by the Merced River, and not a single molecule of that stuff in the entire Merced watershed. And so I don't know how you can argue that that Tenaya Creek or some river here wasn't at some point joined up with a volcano. Yeah.
Thank you.
So maybe it's circumstantial evidence. People in science say you can never really prove anything, so might be an example of that.
Great talk. Thank you. I had two questions. One, how, I may have missed it, but how recent was the development of this new paradigm? And then what was the response from the scientific community to your discoveries and ideas?
So the response varied from silence to rage. And I wouldn't call this a paradigm yet. Still there are literally maybe 4 of us who don't believe in this theory of recent uplift. And so trying to get any of this stuff published is very difficult. And so, so the response has been not great. But there's this evidence is starting to accumulate more and more. So there's a group from Stanford. What they've been doing is they've been looking at how long the Sierra Nevada has created a rain shadow to Nevada, right? Because you have storms coming in from the Pacific, they climb up the Sierra Nevada, they rain out, and then you get this rain shadow in Nevada. And so what they've been showing is that rain shadow in Nevada has been around for like 40 to 50 million years. So that tells us that the Sierra Nevada has been high for at least not long. So, but their stuff, they also have trouble publishing it, and nobody really believes it. So it's we're still kind of, lunatics in the wilderness, kind of. Yeah.
A very interesting talk. I have a question that might not be directly related to what you do.
Uh-huh.
Just curious. So since there have been so many rivers and like creeks that's been cutting through these mountain ranges, and given their age, I'm just wondering if there are lots of like sedimentary rocks as well, and potentially maybe fossils.
Oh, I'm sorry, I didn't totally hear your question.
So given that these mountain ranges are so old, right? They're
Yeah,
ancient,
old, yeah.
and also there are lots of creeks and rivers
Yeah.
cutting through them and
Yeah.
changing, like their path as the volcanic rocks erode back. So I'm just curious as to how much of a sedimentary rocks do they have over there, and also, like, are there any fossils, maybe?
Or any fossils?
Yeah,
Oh,
so it's
oh,
not
yeah, great question.
directly related.
Yeah. So there was a big fossil find so that Merton Formation stuff, those volcanic mud flows, there was a big fossil find maybe like 4 or 5 years ago in the Stanislaus River watershed. And yeah, they found all sorts of stuff. What's that? And what it's, I don't know what that necessarily says about the evolution of the range. I haven't followed that as closely as I should have, but there are definitely fossils out there, and they're saying something. They've kept the sites secret because they don't want people going there and poaching all the fossils. So I haven't been able to check it out myself. But yeah, I'm sure there's a story there, but I haven't. It's an avenue that I haven't tapped into yet.
I think that would be interesting to see how, like, the environment around that too, with the fossils, and seeing how, different environments they have like different set of fossils, I guess. So, like, it would be cool to see how it changes. I'm just curious.
Yeah, no, that's a cool idea, and I've never. Yeah, that's. I think that's a thread that I need to pull on a little bit to see if there's something there. Thank you.
Thanks for your talk. I have a question that's almost identical to Scott's, but for El Cap across the valley.
El Cap, yeah.
So is that a river plus glacier? What's the story on that one?
Yeah, so, all these, so Yosemite Valley, obviously had a glacier through it, and the glaciers obviously did some work. And like I said, rivers cut V-shaped valleys, and then when glaciers come through them, they kind of cut out the bottom of the valley and make them wider. And what's actually interesting about Yosemite Valley, when you go into Yosemite Valley, you have this kind of, we have the valley floor, right? It's just very flat. The bedrock there, they've done drilling and other kind of geophysical things. The bedrock down there is, underneath the valley floor is like hundreds of meters deep. So there's hundreds of meters of sediment in Yosemite Valley. And so a lot of that must have been cut by the glaciers. And so for sure the glaciers deepened the valley even more than what the river did. And also widened at least the base of the valley. Because you've got all those waterfalls coming in. And so those waterfalls I won't say must have, but probably were created when the glacier came through and widened the valley and deepened it. And so things like, features like El Cap, it's pretty easy to imagine that being created by a glacier, at least the lower sections of it. Yeah.
This is a biologist asking probably
Okay.
basic geology. So I'm interested in the volcanic edifice and how that shifted back. Is the idea that that's sort of the rubble from a volcano and then it gets flushed by rivers until it's flushed so much that now the actual elevation of a volcano is further back? Is that the
That's
idea?
pretty much it, yeah. So when you think of a landscape in general, you've got stuff coming in and then stuff coming out. And if you've got more stuff coming out than coming in, then you get erosion. And if you've got more stuff coming in than going out, then you get accumulation. And so when the volcanoes were really going, they were pumping out a ton of sediment, and so things were growing outwards. And then when the volcanism started to slow down, erosion started to get the upper hand, and things started to retreat, just like a coastline retreating backwards. Yeah.
So thinking back to the Table Mountains,
Yeah.
those were actual flows, so that was different. There wasn't that same sort of rubbly material there.
Exactly. Yeah. So that was actually a lava flow. Yeah.
Okay. Do you think there was that material? Like, is that also flushed at the base of the mountains in that area?
Oh yeah, for sure. There's
Okay.
that same Merton formation. But that's expected because we see that Merton formation in the actual Stanislaus watershed. We don't see any of that in the Merced River watershed.
Huh.
Yeah, so that's a big difference there.
Thank you.
I get to ask a question too, right? At least one. I have 10,000, but we'll talk later. And also I was telling Manny how we see rock formations. We just went on a field trip with my class that have, they're 55 million years old. That have pieces of, the ancient Sierra Nevada volcanics, including granites.
Yeah,
so it was already eroding back then.
Right.
So we see that all along the coast, and we're going to see that with my class in the next few weeks. But one of my question is, so you have this 3.5 kilometer of, sedimentary rocks that are made of volcanics.
Uh-huh.
Has anyone looked at provenance in terms of, looking at the levels that dissection of the volcano? Because you can imagine that you start dissecting the lava flows and then eventually get to the core of it. So is there any evidence of that progression?
Yeah, I've wanted to do that because the Merced, all that sediment from the Merced River was deposited in a big fan, this huge alluvial fan. And I've wanted to, go through there and start picking through that sediment and doing,
They're probably
doing stratigraphy.
wells.
What's that?
You can do petrography on the wells. They're well
Yeah,
data.
yeah. The problem is that all the good sites are on private property,
Right.
and it's difficult to access. is the
Okay.
problem.
I wonder though, because earlier in the century they were doing a lot of oil well
Yeah. that's true.
perspective work. So there might be some data because that will show the evolution of
Yeah.
the dissection.
Yeah.
Okay, and then I'll ask you the other questions later because I have a lot of them. Thank you so much for your talk, and thank you guys for coming.